Okay, so today's we are going to discuss the adversarial searches, another topic related to the search problems. Remember, we have studied so far uninformed searches, informed searches, local searches, and when we were discussing the local searches, we discussed the optimization problems, and for the optimization problems, we discussed the genetic algorithm, one different topic, because genetic algorithm solves the optimization problems. And then we discuss the constraint satisfaction problems. Constraint satisfaction problems are also related to the search problems, because we try to reduce the search trees using the some constraints. And we discussed the backtracking in CSPs. Backtracking was for the improvement of search trees traversing through forward checking, through our consistency. We were trying to improve our speed to traverse or to go through the states in the search tree. So adversarial searches is basically, we can also call this the game search algorithms, because this is very interesting. You will see these searches are mostly used to program the simple games that we simple or even complex games that we play in the computers. So getting started, these are some of the examples of the games: the checkers, the chess, the Go, and the Pac-Man. And on the x-axis, you are seeing the games, and on y-axis, you are seeing the different levels in the games. A brick level and human level, expert level, and solved. I will tell you the details about these levels. A human level means the understanding of the game by a human. uh, Whatever a human can do the best in that particular game is basically the human understanding level of that game. I mean, in checkers, how efficiently a human can play the game. Uh, this is the human level of the human understanding level of that particular game. The same way the chess game, complicated game, very interesting game. The human understanding level of this game is called the human level. And what is the expert level? Expert level means uh, any most efficient or the optimal computer algorithm which is more expert than any expert human. And the expert level of this game means, so what does this human level of this game means? Human level means human will try to get the optimal move, will try to get the best move, but there are error chances in human level. Human, in any of the move of the chess, human can take the bad move, right? Or maybe human is trying to get the chance, and for that chance human can take some risk. So this is called the human level. The expert level is basically the optimal level of the game, because expert will always try to take the correct move, always try to take the optimal move. And expert level is of course better than the human level, because uh, so most of the times this expert level we called is the some computer algorithm that is expert, uh, better than human. And that expert can take the optimal moves even better than the human. So that is why we call the expert. And when an expert will compete with the human, we are playing a game with the computer. Computer is an expert's algorithm. We as a human is an expert player of that game. We are playing one game with the computer. If computer beats us every time, it means computer algorithm is more expert than a human. So this is the expert level. Why why expert is more better than a human? Human is the supreme kind of thing in this universe. Then why still expert could be better than a human? A very simple answer. We studied in the very first lecture of the AI course. If you remember, I discussed with you the multiple things related to AI limitations, related to AI strengths. At that moment, I discussed with you there are some natural limitations of human. Human cannot see multiple things at the same time. Human cannot be at multiple places at the same time, right? Because there are no copies of human. And so far and so far there are multiple natural limitations of the human. So this expert is a computer machine. A computer machine can run multiple things in parallel. So that is why, so of course every game will have a tree like solution. You remember we called it search tree. For example, I am starting the game, this is the first move, I have these two options to take next. I can take either this move, I can take either this move, right? Let's say I took this move, and from this move next I have these three options. Let's say I can go here, I can go here, and I can go here. So from this move, let's say I decided that this move seemed more accurate to me, so I took this move. So this is how a runtime search tree is being built for the for the multiple options of any game. We will see multiple examples next. So and of course there will be some ending of this tree. In case of finite search space, a tree will end somewhere. A human, when we are at this stage, in the very first stage, a human can see a limited next possible options. Human can foresee limited next possible options. Human can think of, okay, if I take this move, and next I will take this move, and next I will take this move. So a human can foresee, maybe can assume or can foresee next two three possible moves. But a computer, an algorithm, can save this complete search tree, a complete game tree of that game, and a computer can foresee all the possible next moves before taking any move. That is why we are saying the expert is even better than the human. I hope I made this point clear to you. And then the solved step is even more uh, than the expert. What does this mean? So what we were saying, that a human level expertise of any game means, if a human is expert, human can foresee that what where will the game will go in future. Either this game will tie, or I will win this game, or maybe I have lose this game and my opponent will win this game. Human can foresee next a couple of next moves from this state. Human can see, okay, if I take this move, next could be the this best possible move, and next could be this best possible move. I, in the same way, an expert computer algorithm can see even more moves than a human. But just imagine if this search tree is very big. If this search tree is very big, means it is computationally very expensive to store, then even a computer cannot store the complete tree, right? If any game has a small game tree, and computer can save the complete game tree, and before taking any single move, computer will look all of the next future possible moves. This is called solved. So checkers is solved because checker game has a finite and comparatively small game tree. So we can save the complete game tree of all possible moves of the checkers. That is why we are saying that checkers is solved, completely solved, because we know each and every possible move of the checker, and we can save it in memory, and our algorithm can go through all the possible moves and can select the best possible move. When we talk about the chess, of course, there is some human expertise level. There is some algorithm which is more expert than human, because algorithm can see more choices, more options, can foresee the future moves more better than a human. But check, the chess game is not completely solved yet. What's the reason? In chess, on average, the branching factor is 35, means there could be 35 number of branches at each level, and there are on average roughly 100 depth, 100 number of levels. So now just calculate this figure, 35 into 100. These number of states in the state space of the chess game, the game tree of the chess game exists. So of course, we cannot save this complete. This is a very big, very huge game tree. We cannot save this complete tree in the game. And for each move, we cannot traverse the complete game tree before deciding that which move is best or the accurate. So that is why we are saying chess is not till completely solved. And same goes for the Go, there is expert level, and for Pac-Man, you can think of yourself. I left it for you that Pac-Man is a human level, Pac-Man is at expert level, or Pac-Man is solved or not. So there are some theoretical things now, according to this slide. Checkers in 1950, first computer player was invented related to checkers. In 1994, first computer champion. So 1950, the checkers was kind of was programmed. Computer was able to play the checker game with the human, right? But 1994, the computer player actually becomes more expert than human. So we call it the expert level in 1994. Chino candidate 40-year reign of human champion, Marion Hensley using template 8-piece endgame. 2007 checkers, and in 2007 the checkers was completely solved. Means the complete game tree, the all possible moves of this game was um, was programmed to the computer expert system. And it can see all the possible moves and select the best possible move. Next is the chess game in 1997. There was the Deep Blue algorithm, which actually defeats the human champion. This means in 1997, the chess game was at expert level because this system, the system that defeated an expert human, it means this system is more expert than a human. So in 1997, but this game is not still not completely solved just because of the very large size of the game tree. The same go for the Go game. This is written here, and for the Pac-Man, you can see yourself. So moving next. This is the Pac-Man behavior. This is the Pac-Man board. This is the Pac-Man position. This is ghost position. Pac-Man need to eat all the dots by avoiding these ghosts. So how this will go, we will see in a couple of minutes. So there are multiple types of the games. Adversarial searches are used to develop or to program the games. We will see how we can use this algorithm and how it works. So many different kinds of the games, deterministic or the stochastic. You know about this. We studied deterministic and stochastic on the basis of environment types in the very first lectures of the AI. Deterministic means any game which is deterministic. uh, Chess is deterministic because you are seeing all the next, you can actually foresee all the next possible moves because everything on the board is very clear to you. It is before you. There is nothing hidden in the chess. There could be stochastic games. Um, Stochastic games, the example could be the cards we play. We don't know what cards the other person have in his hands, his or her hands. One, two, or more player games. One player game. Pac-Man is a single player game. We have seen multiple games related to two player. A tic-tac-toe, any other Sudoku and Ludo, many other games. More players could be the car racing games and some cricket tournaments or many other games which involves more than two players. Zero sum games means players are playing against each other. There is no scoring related things. Uh, if one wins, the second will lose. If second wins, the first player will lose. So the two-player game, and both players are playing against each other. Perfect information, you can see the state, kind of deterministic thing. You have the perfect information about the about your environment, at which state you are currently. Again, I have given you the example of chessboard. Any other game in which the environment is very clear to you, it is before you, you are seeing what move you can take. And imperfect or partial information is whenever the games like the cards, and other kind of games in which you cannot see the complete information. We want the algorithms for calculating a strategy or policy which recommends a move from each state. So whatever the state in the game is, the player will have to take the move, of course. And which move will player takes, it depends on the strategy or policy of that player. One player is playing optimally, suboptimally, randomly, or what, this is called the policy of the player, that how a player is taking the moves, how a player is taking the steps. So the problem formulation, just like CSP, you remember, we said there are domain, variable, constraints, right? We decided the problem formulation in genetic algorithm. There were different steps. In the same way, we are now saying that in the deterministic games, what could be the problem formulation? So in deterministic games, we have the states. It is same like the search algorithms. We have gone through the uninformed, informed searches. States, every state is a kind of, in a search tree, every node is a state. So we have a couple of states. Players, in case of one player game, there will be one player. In case of two player game, there will be two players. In case of multiplayer game, there could be n number of players. So players, and then actions, the possible actions that any player can take is going to be the actions. Transition function is kind of similar to the successor function we studied in the previous regular search algorithms. Successor function was, if you input the current state, if you input the current state and you input the all possible actions, what will be the next state? So this is the transition function, or you can also call the successor function like our regular searches. A terminal test is same like the goal test we studied in the regular searches. Means after each move, when you have a new state, you will check that your state is goal state or not. If it is goal state, are the terminal test in this particular example, we will stop. The terminal utilities, it is kind of similar to the evaluation functions in the regular search algorithms. Terminal utilities mean there will be some utility functions. We call it utility. I will tell you why we call it utility. These functions are called the utility functions. We check that what is the best possible scoring value if I will take this move. And if I will take the second move, what will be the best possible scoring value, utility value I will be getting. So your terminal utilities are basically the evaluation functions, utility functions to evaluate the states, which state is good or not. Solution for a player is a policy. So again, we discussed in the previous slide. Here we are trying to trying to define a best optimal policy uh, to take, or to play the game, or to take the moves. So this is called the policy. Then next, the description of zero-sum games and some general games. I already discussed with you. This is very good example. You can see there is a single diamond. There are two players. This player is trying to get this diamond. This player is trying to get this diamond, same diamond. If the blue player gets the diamond, blue player will win. And in case of one player's win, the second will automatically lose. So this is called the zero sum games. When one body wins, the other body loses. If the other body wins, then the first body loses. So this is called the zero sum games. Agents have opposite utilities, values on outcomes. Let us think of a single value that one maximizes and the other minimizes. So what maximizes and minimizes means we will see in a couple of minutes. Adversarial and the pure computation, these are the zero-sum games. And in the general games, agents have independent utilities. For example, out of these number of states are the, you can say, the search tree are the uh, moves. The blue player is trying to collect the green diamonds, and the red player is trying to collect the orange diamonds. And both are trying to optimize, both are trying to maximize the count of their own diamonds without affecting the other player. So the win or the optimality will be decided on the basis of the maximum number of counts, maybe in the smallest number of time. Uh, this could be the output, that which player got more diamonds in less period of time. Maybe there could be other values, other settings of the game as well. So we call the competitive environment in zero sum games, and here we call the cooperative environment in the general games, because both are independently working without competing with each other. Okay, then in adversarial searches, okay, we are starting from the single agent games, single agent trees, which means the one player game, right? So, considering this example, the Pac-Man can move left, right. You know about this. Pac-Man has to eat the white dot. Let's say we have the score um, of the movement of the Pac-Man. Pac-Man's one move consumes -1, right? Either it's left or right, whatever the direction is. One Pac-Man moves cost -1, and if Pac-Man eats one white dot, it actually gives the +10 score. For example, these are the scores in this particular single agent tree. So how many options we have after this state? We have two next possible options. Either Pac-Man will move right or left. And what's next? From this state, we have next two possible states. Either you can move further towards the left side or towards the right side. And from this state, you have the options to either you move left, either you move right. How we calculated this score? It is very easy. The Pac-Man at this state, Pac-Man moves one step, so there is -1 score at this state. The Pac-Man moves one step right, there is -1 cost consumption. When the Pac-Man moves further one step away, so it is again -1, so -1, -1, -2 cost here. And again, if the Pac-Man moves backward, so -2 cost here. And at this state, if the Pac-Man moves again one step backward, there will be the -2 cost here. And if Pac-Man moves forward, there will be -2 cost here, but there will be +10 as well, because Pac-Man eats one white dot. So -2 plus 10 is actually equal to the +8 cost of this particular state. In the same way, if you draw the complete game tree of this single agent game, going down, going down, going down. So these are the assumed scores, just written to for your understanding, that this will have 2, this will have 0, this will have 2, 6, 4, 6. Of course, we need to go to the complete end of this search tree, and then we can calculate the scores. So these are the scores actually. Oh, interestingly, when we allocate these scores, there are there are couple of terminologies that we need to understand first, and then we will see what uh, we are going to discuss next. So value of a state, the best achievable outcome or the utility from that state is called the value of a state. The value of the previous states, the value of this state is 8, the value of this state is -2, the value of this state is -1. And interestingly, the values in these game trees are starts from bottom to top. from the leaf nodes towards the top node, because until or unless you did not decided that if you will take this move, then this move, then this move, you will win or lose. You cannot say that I'm going in a good way or bad way. So we need to see the complete path till end. Then on the basis of win or loss, it will depend on the game. You have seen the types of game previously. If it is zero sum games, so we will have three possible options: win, lose, or tie. If it is a general games, we will have some kind of scoring, diamonds collection, number of diamonds, total number of diamonds, something like that. So in that case, we will have the different scoring criteria. But scores will be at the very bottom. We call it the leaf nodes. And in this particular topic, adversarial searches, we call it the terminal states. Terminal states because the terminating states, you cannot move further from that state. Either you tie, either you win, or you lose. And you propagate the values backward from the leaf nodes towards the upward. And from this, so each score is basically the value of that state, and the leaf nodes are called the terminal states in adversarial searches, and the other states, those are not the leaf nodes, are called the non-terminal states in this adversarial searches topic, right? So interestingly, what you have seen in this example is this is a single player game, and what do you think, which path this particular agent will take if it plays optimally, if it runs optimally? So which path this Pac-Man will take out of these all possible paths? Let me erase a little bit first these paths, so let me clear it to you what I'm going to say. So out of these possible options, this Pac-Man has this one option, this this Pac-Man has this second option, this Pac-Man has this third option, this Pac-Man has this fourth option. What what option this Pac-Man will take if it runs if it runs optimally at the best moves?
सर राइट सब ट्री के पास जाएगा.
This eighth one, right? Yes. Uh, because the objective or the end goal of this agent is to eat the white dots to get the maximum score. If we program all these possible options and we ask or we traverse or we search the best you can say the moves, of course this Pac-Man will take these moves because these are the best possible moves. In the minimum time, you're getting the best score. Now, interestingly, when we say that we are moving towards the two-player game, the tree is kind of similar, but the moves in the tree changes a little bit. Okay, so this is the initial state or the starting state, or you can say the start state of the game board, and you are getting started. What are the options that Pac-Man have from this state? The two possible options: either move the left side or move towards the right side. Okay, and in the next step, interesting. Now, actually, the move is of the ghost. When we are saying that we are playing the two-player games and we are playing the zero-sum games, there could be fair values or the fair options available for both players. Otherwise it is not a good game. It is not a fair game. It is not a fair competition for both players. For example, if you say that we are playing a competitive game with another player and we are saying no, I will take two moves, you will take one move. This is not fair. The grounds of the game will be similar for both players. Then we will decide that which player plays optimally and which player won, which player lost, whatever it is. So in this particular example, we are seeing that the first move was taken by the Pac-Man, and then from this state, the second move was taken by the Ghost, not again by the Pac-Man. Yes, we can decide this particular step in a different way as well. For example, I will take the three consecutive moves, and then you will take the three consecutive moves. And this kind of other settings can be made until or unless both players are agreed to that game settings. What we are saying here is a simple scenario in which we are saying that uh, in the game search tree, the one move will be of one player and the second move will be of the second player. Another question arises here is which player will take the first move, because sometimes in some games the first move becomes decisive. uh, like we sometimes assume in cricket that the team which won the toss uh, highly chances of win because it is elected to, let's say, bat first. So but again, this is kind of assumption to us that which player will take the the first move. And just like cricket, we have some answers to this particular problem. This is not a big problem. We can select it randomly. We can roll a dice. We can toss just like cricket to decide this thing so that both players are agreed on it. So there could be a couple of other methods to decide this thing that which player will take the first move. This is not a big problem. Okay, so when we are saying that there are two options with the Pac-Man selected left or right, and then from this state, the Ghost has the two options left or right. The same way from this state, the Ghost has the options left or right. The same, we will continue, and of course, till the end of this game tree, there will be some terminal states, and there will be some scores on the terminal states, right? And now you need to see, for example, Pac-Man will take which move? The left one or the right one from this state? This is what we are discussing now. This is what the importance of game tree is. This is what the importance of these utility scores is. How we will decide that Pac-Man should move at this state or at this state, because out of these two states there is only one thing that is very clear to us, and that is in one way we are going towards the ghost and in other way we are going opposite to the ghost. But another important thing is, in one way when we are moving towards the ghost there is a white dot, and when we are saying that we are moving away from the ghost at this state, there is no white dot at this state. So this is kind of a very difficult situation to decide. Either we have to move towards the ghost and the white dot, or away from the ghost or the white dot. So these are the complicated situations in which actually the importance of this adversarial searches and the algorithms that we are going to study next are come to help us. So from this particular example, what you can see, a very easy way to do this is, let me show you. So do we have two players? First, we need to decide which player is trying to maximize this score and which player is trying to minimize this score, because this is a zero-sum game and it is very obvious that, of course, one player is trying to maximize and the second one is going to minimize. In other words, one player is trying to win and the second player is trying to lose that player. And if one wins, the other will automatically lose. If one lose, the other will automatically win. So Pac-Man is trying to maximize the score and Ghost is trying to minimize the score of the Pac-Man. So from the terminal states, because this is the Pac-Man move, this was the Pac-Man move, this was the Ghost move, this was the Pac-Man move again, and going so far, until you get the terminal states. In other words, Pac-Man is trying to maximize. So this is the max move. Ghost is trying to minimize. So this is the min move. And this is again going to be the, sorry, min. I have to write it like that. This is the min move. And this is again the max move. So if we consider this the max move, what value you will get here? -8 out of -20 and -8, which is the larger value? -8. This is -5. What you will get here is 4. What you will get here is 8. This is the min move, the ghost move. Ghost will get the minimum value. You will get -8 here out of -8 and -5. -8 is smaller, minimum. And out of these 4 and 8, you will get 4 here. This is again the max move, right? So you will get the 4 value here. Out of the -8 and 4, you will get the max value, and that is 4. And on the basis of this value, when you have gone from bottom to top by passing all the values of the terminal states upwards, now you can decide which move Pac-Man should take. So Pac-Man should move towards this, and then this, right? This is what we come up after applying a simple technique, and this technique is called the min-max values. We decided that one player is the max player, the second player is the min player, one move is of the max player, and the second move is of the min player. Which particular uh, state we will select on the basis of the scores, and we move on. This is the same game tree, but here we calculated these values on the basis of the Pac-Man moves already discussed with you. Each move cost -10. One white palette it is +10. So on the basis of uh, this, you can calculate these scores, and you can apply simple Minimax algorithm on it, and you will be able to get this values. So the max is the Pac-Man's control, and the min is the opponent's control, and the terminal states are the final states which has the scores. This is another example. The tic-tac-toe game, very easy. Maybe most of you familiar with this. The goal is to uh, arrange one player's uh, column wise, row wise, or diagonal wise, same settings. For example, if O player arranges it like this way, O player wins. If X player successfully first arranged this way, X wins. These are the two players, each of these trying to block the other player's state and arrange our its own values in the correct way. So this is the game. Most of you familiar with this. What we did is we decided that this is the move of X. So from these 9 at the very start, all of the 9 boxes are empty. This is the X move. So X can place anywhere out of all these 9 places. And once X is done, let's say X chooses this move, very first placement, then it is the O player's move. So O has the 8 options left. 1, 2, 3, 4, 5, 6, 7, 8. So O can place any of these And then uh, next is again, for example, these are the three possible states we selected for the O. Of course, there will be eight possible next states, successor states, transition states from this state. And after this, we again have the X players move. Until or unless you reached these states, and these states are called the terminal states because there is no next states possible, and you can calculate the score as well. From this, O player arranges successfully three in a column. So O player was min player. That is why we are saying the -1 score. And from this state, there is no one successfully arranged. So it is a tie. We give the 0 score. And this is when successfully X player arranges. X was the max player. So we give it the +1 score. We can swap it. X could become the min player and O can become the max player. There is nothing wrong in this. You will get the same output in this case. One thing that you realize after seeing this tree is this is a very simple and very small space game. 9 boards, 9 states in one board. But just imagine the total number of states that we have seen even in this 9 state board. We're not able to show all those states in a single slide, but you can assume 8 possible states from this one move, 8 possible states from this, 8 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 from this, and 8 from this. And next, 7 from this, 7 from this, 7 from this, 7 from this, so far. Next, 6 from each, right? Just imagine the size of game tree. That is why we are saying the next thing that we are going to see is the efficiency in the traversal of the game tree. We cannot do this way like we did in this particular Pac-Man's problem, that we will see each and every option until the terminal states. We will see all possible states until the terminal states and then select the best action. Just imagine this size of game tree, and then for taking each move, you have to see that if I will take this move, you have to completely traverse the tree till end to check that if I will take this move will lead me towards the win, tie, or loss. If you will take this move, you will check the complete tree till terminal states. If I take this move, I will tie, win, or lose. If you are able to see the complete tree from each particular next possible option or the state, this is what we were calling the solved state. The complete game tree is understandable and solvable. This is what we were saying in the very first slide, that if we can program, if we can save the complete tree of the game, and before taking any single move, we check the complete tree, this is called the solved stage of any game. But what we call the expert means we are not going through the complete or all possible next future states until the terminal states. Still, we are taking the best move. It is called the expert state. And human is basically on the basis of logical reasoning, on the basis of game understanding. Human is saying that I will take the most optimal move, but that could be wrong move in some scenarios. That is why expert can beat human. And if the game is completely solved, interestingly, if the game is completely solved and both players know the complete solution of the game, the output of that game every time will be tie, because each player will try to get the most optimal move. In this, even in this tic-tac-toe game, just imagine this game is completely solved. Both players, Max and Min, knows the complete solution of tic-tac-toe. So before taking each move, X will go through all the possible states until terminal states. Same goes for O. O will see all the next possible states until terminal states. This game is going to be tie in every match because both players are playing optimally. One has to make any mistake so that second can win. If one wins, of course, the second will lose. Hope you get this point. Second important point from this slide is just imagining the size of this game tree, even a very small size, 9 board size game has a very large search tree, the game tree. Imagine the board size of the chess game and the search tree size of the chess game. Just imagine. And the Minimax algorithm that we studied previously, and we will see the example of this in the next as well. This symbol shows the max move. If the diamond is upwards like a triangle, it is max move. If the diamond is downward, triangle is inverted, this shows the min move. So if you see the Minimax algorithm from this particular slide, you are getting another idea. Can anyone of you tell me which search is similar to the min-max algorithm? If we apply the min-max algorithm on this particular game tree, it is similar to which search algorithm? It is easy. I don't know why you are not getting this point. So what we are doing? See here, this tree. It is the max player move, it is the min player move. So min will take the min value, and which is out of 8 and 2, which is minimum 2. Out of 5 and 6, 5 is minimum. This is max player's move, and max will take the 5 value. So the path of this game will be uh, this. This is the path of the steps in this game. In case of Minimax algorithm, we are saying that a player will select one value, go next. We'll see the next possible values. Go next. We'll see the next possible values. We send the values backwards, and then next value, next state, next state, next state. Send the values back, terminal values, and then move next and move next. Which algorithm is this? It is similar to a depth first search. You are going up to one depth first until the terminal states, getting the scores or the utility values and going back. Then next branch and going till the depth of that branch to get the terminal values. And then next and then next and then next. And we are saying when we were discussing the DFS, we discussed that the DFS has the time and space complexity of b raised to power m, if you remember this, right? We will see in the next slides. And b raised to power m is a very big complexity. So solving the games like this, which has a very big game tree, with that bad time complexity of b raised to power m is going to be infeasible for us. That is why we even need to improve this min-max algorithm. You are with me so far or not?
Yes, sir.
Okay, thank you. There was a peak silence. I was even in the impression that nobody's here. Okay, so so now we need to see that what we can do in the case of Minimax improvement. How we can improve this algorithm so that we can traverse the large game trees as well. This is another example of Minimax algorithm. This is the max move. This is the min move. Going down, these are the terminal states. You got the 3 value, you got 12 value, you got 8 value. This is the min move. What value you will select out of this? Because this is the min move, you will get the 3 value, minimum of all these. Then this is again min move 2, 4, 6. You will get the minimum value and you will get the minimum value. Now this is the max. Max will select the maximum value out of 3 to 2 and you will get the 3 value. So the time complexity of Minimax algorithm is equal to the DFS and b raised to power m. The space complexity is going to be bm. And imagine for the chess game, it is going to be 35 into 100. I already discussed with you. Just imagine the game tree of this size and this bad time complexity. It is almost infeasible to solve. That is why we need some better algorithms as compared to Minimax. Okay, so if we consider Minimax, I discussed this thing with you. If we consider that both are the perfect players, then the game is going to be tie in 99% of cases. Both are playing optimally. One is trying to defeat other, second one is trying to defeat other. Maybe one is trying to win from the other and second one is also trying to win from the other. So both are playing optimally. Both are taking each move by going through all the search tree completely. Of course, in this particular way, the game is going to be tie, the draw. If any one of the player make mistakes, then there are chances that the other player could win because of the one or the bad move of the other player. So if you are playing the game with a very mastermind of the player, of course the game is going to be tie. If you are playing the game with an average player like you maybe, then there are chances that we can get the win, or second player can get the win and we can lose. So what are the options when we say that we will not take the perfect move? It means, what does this mean? If we say that each player will take the perfect move, it means min will take 10 value here and 9 value here. Max will get the 10 value here. Now just imagine a different settings. For example, this min player taken the bad move and selected the 100 out of 9 and 100. Here you have 10 and 100. Of course, Max will get 100. Max is going to win in this case. In which case the min player will take the 100 value, not the 9 value. So this is what we need to see. We will see this in our next lecture. We are not going to be in this detail today. We will see in the next lecture. Min can take this move, this particular move in because of 2 3 different reasons. The one could be min is trying to take some random move. Min is trying to get some chance. Min is trying to just see that which strategy the max player is playing with, and couple of other reasons as well. We will see later on. So because of the resource limits, we discussed that the Minimax algorithm is similar to the DFS, and if we have a very big game tree, it is going to be almost infeasible to solve. So this is the resource limit that in realistic games, of course, we cannot search until the terminal states. So what are the options now? There are there are two possible options. One is, can you calculate the estimated scores or the estimated utilities at this state rather than going towards the end? This is the one possible option. Just like the heuristic functions, remember we studied in inform searches. We were guessing on the basis of partial information, we were calculating some heuristic values. So can we calculate the utility scores intermediate or kind of after 3 steps, maybe 10 steps, maybe 50 steps, rather than going till the end of the terminal states? The second option is, can we do something like A star algorithm or something like UCS, that we avoid some complete paths? Those are irrelevant to us. We have no need to visit this path. So these are the two possible options that we have to see next. And if we successfully able to do this, this will of course improve the Minimax algorithm's complexity. So the one could be the depth limited search. You can apply some limit on the depth and you can calculate the estimated utility scores. Of course, these are not the actual utility scores. These are the estimated utility scores. The best your estimated utility function is, the best you will get the estimated values and the best chances of getting win. If the evaluation function or the utility function is not good, you are not going to win using the estimated values. So the guarantee of optimal play is gone because you are not going until the end of the utility states, and there are chances that you are not going to win the game. So optimality is not guaranteed in this particular scenario. More plies makes a big difference. More plies means if we stopped here, if we go one step down, one branch down, it will add a lot of other states to be explored. If we go two step down, it will add a lot of other states to be explored. The same way we are going. So one option could be, we can use the iterative deepening algorithm. Like if we get the solution here, stop. If not, go one step down. If not, go one step down. This is kind of the things, and calculate the estimated utility score at this state, estimated utility score at this state, so far and so far. So evaluation functions are always imperfect. Evaluation functions, because these are the estimated utility functions, so of course these we can say that these are the imperfect. The deeper in the tree the evaluation functions is buried. Yes, this is very good point. If using iterative deepening or any DFS algorithm, we are going down, then there are no benefit of using the estimated utility functions, because actually we are going very near towards the terminal states. What's the benefit of using the estimated function? So the deeper in the tree the evaluation function is buried, no benefit of using those, because you are going very near toward terminal states. So you should actually use the terminal functions rather than the evaluation or estimated function in this case. And these are some of the examples you will see, you can see in your own time. um, Demos, evaluation functions. Yes, this example is interesting example, the Pac-Man starvation example. This is the state. Interestingly, what are the next possible states? There are two next possible states. One is Pac-Man move further left. The second one is Pac-Man moves one step back. So again, same things. One Pac-Man movement is -1 score, and one white dot eating is the +10 score. Why Pac-Man will starve? Because it is interesting. If Pac-Man moves one step here, the cost is -1. Here you will get the -2, -1. Here you will get the -2, one step, and here you will get -2, but you have eaten one dot, and that is going to be +8, and you will, sorry, +10, and you will get the, let me raise that, very hard to write here. Okay, so -2 plus 10, and you will get the final score of +8. Sorry, we have written something wrong here. There was the white dot. Yes, at this state. So it will be -1 plus 10, and you will get the score of 9 at this state. Hmm, yeah. So this is going to be, no, this is 2 steps away. One step is missed actually. One step and +10. Yeah, it's okay. 10 plus -1, so you will get the 9 score at this state, and 9 minus, now we will say this -1, not -2, because we have subtracted -1 here. So this is -1, you will get the final 8 here. You have the final 8 here, you have the final 8 here, and you have the -2 here. So on the two sides, you have the similar scores, 8 and 8. So Pac-Man is confused, either it should move left side or the right side. This is the starvation stage. Of course, in these particular scenarios, we need to decide that we should move at what stage. There could be multiple solutions of this. Remember, you are getting the positive value before as compared to this path. You are getting the positive value after 2 steps. On this path, you are getting the positive value in the first uh, step in this path. So we will prefer this path. Either the accumulated or the calculated final score is similar to this side, but this side is getting more quickly as compared to this side. So if there is something like this in your games, you can little bit mold, little bit alter your evaluation functions or the scoring functions by adding some extra benefits of getting the uh, faster scores at the goal states. Okay, these are the demos. You can see it yourself. And yes, this is the chess game. And in chess game, the evaluation function is, for example, the position of your queens, the position of your horses, the position of your all other particular black queens, white queens, your all scenarios, what are here. You can sum up the scores of your all particular points, and the other player will sum up the values of all its values, and you can calculate the evaluation score, and in this way the same minimax algorithm can be traversed on this particular search tree. So we discussed the one solution of minimax, and that is, if we don't consider the complete tree, we don't want to go until the leaf nodes or the terminal states. We can use some evaluation or the estimation functions to calculate the estimated values, and in that case we will not going to be in the depth of the tree. The second option is the game tree pruning. So what does this game tree pruning is? It is very interesting, little bit complicated, but good algorithm. Just like we were discussing, I give you an example that an A star algorithm, you avoid the unnecessary paths. The same way, can we do some kind of pruning by removing the unnecessary moves, or the moves in the game tree those are not going to be in my favor by any means? How we can do this? For example, in Minimax, we have gone through this algorithm example already. You need to focus on this example for just a couple of minutes and you will get the idea. So the idea of alpha-beta pruning is in Minimax algorithm, this is the max move, this is the min move. So the min will select the value 3 out of all these possible values, interestingly. And now this max, just focus on this. This max has to take the value 3 are greater than equal to 3. What I'm saying, if this particular state gives the value 4, of course max will take 4. If this particular state will give the value 2, will return the value 2, max will not take the 2 value because max have to take the max value. So if it is 3, 2, 1, max will consider 3. If it is like, sorry, okay, if it is like this way, if it is 3, 4 and this side let's say 7, max will prefer 7, of course. So now focus on this. This min is saying that min only check the first terminal state's value and it is 2. If this value is 1, only in this case min will override the 2. Agreed? Because min has to take the minimum value. Or if this next state has the value, let's say 3, this 1 will not be overwritten by 3 because min has to take the minimum values out of all these 3 values. So if the first value coming to this state is 2, it means if this value coming from this state is 2, it means this value will be only overwritten or replaced by the value which is going to be less than 2. Right? And if the value this min has is 2, max will only take this value if it is greater than 3. This simply means if the first value is 2, now this value will not be overwritten until or unless you will get the value that is even smaller than 2. But this min is looking for value greater than 3. Right? So in this case, we are saying that if the mean value is 2, we are seeing or we are exploring from the perspective of max player. Max will say, oh, I'm not interested in this because when max will see the 2 value here by the first leaf node, by the first terminal node, max will say this 2 will only be overwritten if there will be any value because this is the min. Min will not allow 3 to come here and override the 2. Min player will not allow this 3 to come here. So if the first value is 2 here, min will only allow to override the 2 if any value is less than 2. Max will say, I already have 3 value. I am interested in any value which is going to be larger than 3. So I have no need to explore this remaining tree. I have even no need to traverse or explore the values, the terminal values of the other states. Because I know min has taken the 2 and now min will only override this true if it will take the value even less than 2. And I am looking for 3. Then there is no sense of looking for the values, other values. In the same way, you will get this idea. very quickly again. 2, 4, and 6. Okay. If we are applying simple minimax algorithm, min will take 3, min will take 2, min will take 2. And this is the max move. Out of these options, sorry, out of these options, max will take 3. So if you use minimax algorithm, you will get the value 3 at the top. I am talking from the perspective of max move, the first player move. Player 1 is looking all the tree, player 1 is looking all the possible moves because player 1 has to decide which move I should take. We are looking from the perspective of player 1, right? We are looking from the perspective of max player. We applied minimax algorithm, we gone through all the terminal states and we get the value 3. The alpha beta algorithm is saying, I gone through these states, first this path, this path, this path, the value is 3. Min will override this 3 because this is the min move. Min will only allow if any value is further less than 3. If we not explore these states, we cannot say that any other states have value less than 3 or not. So that is why we need to visit these states. We will see 3, then we will 12, and then we will 8. And we, of course, min will allow only the value 3. And this 3 will be given to the max player. When max will come here, max will say, okay, what value can I get from this branch? And the min player will say, the first value we got is 2. The max player will think, okay, if min has taken the 2 value first, now min will only allow or the override value which is going to be less than 2. But I am not interested in even 2. I take the value that is going to be greater than 3. So that is why min have no need to even visit these other two states. So these particular states will be removed from the tree, will not be explored from the game tree. And you will get the value 2. The same way when we will go here, let's see here, when you will come at this branch, max will come at this branch, max will say, okay, what value I can get from this branch? So first of all, min will take 14. So max will say, okay, yes, 14 is greater than, okay, I can take 14, but let's see first other values. Will min allow me 14 or not? Min will check, okay, I can take value which is less than 14. Next is 5. Yes, I can override the 14. Min will say I can give 5. But stop here. Let's see the other values as well. Because still the 3 is less than the 5. Max can accept this value. That is why we are saying the other way. We are seeing the other values as well. 5. Okay. Let's see what is the next value, which is 2. Still 2 is less than 5. Min will override this and finally give you the 2 value here. So the value that max can take from this branch is 2. But of course, max will not take this value, will not override this value because max is looking for the value which is greater than 3. So you will get the final answer 3 at this stage. So what you have seen is, in case of Minimax, we were getting the value 3. In case of alpha beta, we are getting the same value 3. The efficiency is we have no need to visit these states in case of alpha beta. So we have removed successfully some unnecessary states. And you will practice this, you will get the idea. It is easy, but a little bit complicated. When you will practice 2-3 different questions, you will get the idea how you can prune or remove the unnecessary states or the nodes. This is written the simple alpha beta pruning algorithm for you, that how we can actually prune, how we are doing this. So if this is the max move, this is the min move, this is the max move, this is the min move. So we are basically trying to prune any particular state which seems unnecessary to us. This is the algorithm of alpha beta pruning. We have seen the Minimax algorithm in previous slides. So this is for the alpha beta, and this is its implementation. The properties of alpha beta is this pruning has no effect on min-max values. You have experienced this in the previous example. Min-max was giving us the final value 3. Alpha beta was also giving us the final value 3. And for the intermediate nodes, yes, if we say that the intermediate nodes might have the wrong values, then there are chances. But this is a very, very less chances that the intermediate nodes have the wrong values. It could be only on the basis of if you are applying both techniques in parallel. You are applying alpha beta pruning and you are using the estimated utility function values, then there are chances that because your estimated utility values was wrong, then there are chances that the alpha beta pruning has selected the wrong values and will give you the wrong particular answer. In that case, minimax will also give you the wrong answer because of the wrong estimated utility values. But the time complexity has been reduced half of the m, because in simple minimax it was b raised to power m and now it is b half of m. But if we still consider that after applying the alpha beta, can we solve the chess completely? Still hopeless. Even using alpha beta pruning, we cannot solve the 35 raised to power 100 size of chess game tree. This is another example of the alpha beta pruning. We use two variables for the alpha beta pruning. This is just for your easiness. This is the algorithm. We start from negative infinity and positive infinity. Alpha is the negative infinity, beta is the positive infinity. In case of max player, we try to change the values. Alpha is max player is going to get in, and in case of min, we try to change the beta values, the positive values. So you got the three value, beta will be changed, and there is a simple condition of the pruning, which is alpha greater than equal to beta. On the basis of that condition, you pruned actually the alpha beta search tree. This is again another example for your practice. So what I will suggest is first go and implement the minimax algorithm, get the answer of min-max. So min will give the 8 value, the 4 value, and max will get 8 out of 4. Then solve it using alpha beta pruning. You should get the similar answer, but some unnecessary states will be pruned. So in this example, what we are saying is we start from negative infinity and positive infinity in the very first state. Alpha is negative infinity, beta is positive infinity. At max move, we update alpha, and at min move, we update beta. And the condition of pruning is alpha is greater than equal to beta. Or you can reverse this condition, beta is less than equal to alpha. That's it from my side. If there is any question, please go ahead.